In Lesson 26, we'll talk about how the cantilever spring constant affects surface force data. And I'm going to pull in ideas from many previous lessons about van der Waals forces, about capillary forces, about interaction potentials, the instabilities, equilibria, etc. Here, I've sketched a van der Waals-like interaction taken with a stiff cantilever. What would it look like if I were to switch to a weaker cantilever and had a perfect measuring system that could show you all equilibria? It looks like this. Wow, that's different. Well, you remember from a few lessons ago that the slope is minus the spring constant of the cantilever if the cantilever is weak. But now we have this region here that has 3 values of force. So what's going on there? Remember in Lesson 19, I was talking about potentials and how potentials can have 3 equilibria, 2 of which are stable. So in other words, 2 valleys and a hill. Well, this region between the blue bars that we say is triple valued in force, each one of those levels of force corresponds to one of those 3 equilibria. So the top one is stable, corresponding to the equilibrium closest to where the cantilever has its free equilibrium position. The bottom one is also stable, and it's the equilibrium that's farther out. And then this middle level, these equilibria correspond to the unstable ones. So you don't see the tip of the cantilever there. What happens instead is that the cantilever comes along the top trace, and then when it gets here, because the next option is to be so unstable, well, that doesn't happen. It's like balancing a pencil on its point. It jumps to the bottom level that is stable, then loads up, then you withdraw the scanner, and you start to unload, and then you come along here. There's no reason for it to jump up. It follows the stable path, and then again here it doesn't want to be on the unstable path, and so then jumps up once again to the stable one. So there we have an alternative explanation for this shape of force curve. Okay. Why am I introducing this again now? I've been over this topic before. Why am I introducing it now after we've talked about van der Waals and capillary forces? Since I've exceeded my capacity as a sketcher, I'm now showing you screenshots of a computer lab program that I've written to help students understand these difficult topics. So here again we have force as a function of scanner position, and the computer has sketched in green a van der Waals interaction and in yellow a capillary. These data were calculated assuming a 10 Newton per meter cantilever. And if you notice, it's the middle third of the data that the van der Waals and capillary look different. If you have a van der Waals interaction, you would follow along the green line both for loading and unloading. And for capillary, during loading, you would follow along this line and along this line for unloading. So in other words, with a 10 Newton per meter cantilever, you could see a difference between van der Waals and capillary interactions. And these data were calculated assuming a 1 Newton per meter cantilever. You see the same idea here. This is the triple valued region of force. And when you consider the instabilities, the cantilever would jump from here to here after coming in along this way. And you would load and unload, and then come along this way. You get to this point and jump. And so you have this 4-part hysteresis loop. It's the same hysteresis loop for both van der Waals and capillary. In other words, very important point, you cannot tell what surface force is operating if you have such a large hysteresis loop because of a weak cantilever. Thus, if it's important to your experiment to know what surface forces are operating between your tip and your sample, you have to have a stiff enough cantilever in order to detect the difference.